Okay, so let me repeat actually what we were doing. Okay, is it visible now? Can anyone confirm?
Sir.
Yeah, thank you. So as I mentioned, in January, NIST asked for replacement of DES, and in September 1997, formal call for proposal was released, and requirement was that length of the block cipher should be 128 bits, support key length should be 128, 192, and 256 bits, and should be available worldwide. Submission was due on June 15, 1998. August 20, 1998, out of 21 submissions, 15 met all the criteria, and first AES candidate conference held for discussions. Another second AES conference was held in March 1999. Okay, and then in August 1999, August 1999, 5 candidates were chosen. Chosen by NIST, and I think I can mention 5 of them. One was Mars, RC5, RC6, then Argendel, Serpent, and Two Fish. Now this was from Belgian scientists. Others are some of them from US and outside US. So basically, this was selected further in April 2000. Third AES conference was held. Okay, and in October, finally, October 2, year 2000, this was selected. Okay, as AES, Advanced Encryption Standard. Okay, so this was developed by 2 scientists, Belgian researchers. Okay, I think Damon was his name, and okay, so finally in February 28, 2001, NIST draft was released. FIPS, Federal Register for AES, was available. And in November 26, 2001, this was adopted as standard. Finally, December 4, 2001, published in FIPS 197 as in the Federal Register. So this is a brief history of this AES, and what were the selection parameters. I should mention some of the selection parameters as are there. The first one was security, cost, algorithm, and implementation character. Okay, so these were the 3 main selection criteria, where actually the last one, this one actually won the selection process. So I'm going to describe this in details. Okay, now as you know, so it's a iterated cipher, and the requirement was that there are 3 keys support. The support key length should be 128, 192, and 256. So what they thought that for each key bits we will have different number of rounds actually, this length is fixed, but for each of these 3 qubits, for each of these 3 types actually, I would say, so there were 3 kind of AES 128, AES 192, and AES 256, okay, based on these key length support, So I'm going to describe a general procedure, and in particular, I'm going to look at AES 128 in details. Both of them, rest of them are similar. The only thing is that the number of rounds are different in each AES. So here is, you see, as you can see that for 128 cipher key, number of rounds are 10. For 192, number of rounds are 12. For 256, number of rounds are 14. Okay. So what are the rounds? The rounds are almost identical. First and last round are different actually. So input is 128-bit plain text. As you can see that 128-bit was a requirement, right? That length of the block cipher should be 128 bits. So in 128 is a input bit. Okay, input bits. Now the first round, before first round, there is what is known as pre-round transformation. In the pre-round transformation, whatever 128-bit plain text is coming, it is XORed with this key K0. So actually, this cipher key, whether it is 128, 192, or 256, is expanded into NR plus 1 key. So suppose the number of rounds are 10, so there will be 11 keys generated. If number of rounds are 12, 13 keys will be generated. Number of rounds of 14, 15 keys will be generated, or sub key, by this key expansion algorithm from the cipher key. Okay, in each of these 3 cases. Okay, so the first thing is that in the pre-round transformation, a round key K0 is XORed with this plain text bit, 128 plain text bit, right? After that, so for example, in this case, suppose we focus on 128 key size for the cipher key. So we are picking a 128. So there will be 10 rounds here. Okay. So now more or less we are focusing on 128 cipher key. So there are 10 rounds here, and last round is slightly different. I'm going to tell you how the last round is different. Okay, so how many rounds are there total? 10 rounds plus 1 pre-round transformation, so total 11 rounds, in 128 cipher key. Any question at this point? Because I think this is a little bit lengthy, so it is better if you interact with me so that you can better understand it. Okay, now this is a high level description, as I mentioned. So key expansion mechanism is there. Round keys are derived from the cipher key using a key schedule. As I mentioned that, how many keys will be generated if round is 10 round, 11 keys will be generated. Okay, fine. Initial round, we add round key. Each byte of the state is combined with round key using bitwise exclusive OR. Okay, so initial round is like this. Pre-round transformation is like this. Okay, then after that, round 1, round 2, round 3, and so on up to round 10. So before round 10 up to round 9, all things are similar actually. So then in the intermediate rounds, we have these 4 transformations. SubByte is a nonlinear substitution map, shift rows, transposition step, mix column, mixing operations of each column, and add round key. These 4 of them are the major transformations that happens in each round. And the final round, there is no mix column, and these 3 things are happening: SubBytes, shift rows, and add round keys. I'm going to explain to you what are SubByte, shift row, mix column, and add round key, but this is the general picture. So basically we have round 1, round 2, round 3. So pre-round, this is pre-round, right? Then round 1 to round 9, we will have this, and this is round 10, final round, right? So total 11 things are possible, and basically for the case when there is 128-bit cipher key is used. Okay. Now let us look at what are these SubBytes, shift rows, mixed columns, and round key. So here is the overall structure. As I mentioned, this is pre-round transformation. Plain text 128 bits are going here, right, as an input. Add round key. So basically, cipher key is W0, W1, W2, W3 are added. I'll explain to you what are these WIs and how we can get them. Then we have round 1, SubByte transformation, shift row transformation, mixed column transformation, and round key. Similarly, in round 2, round 3, round 4, all these things. And then add round key means the cipher keys W4 to W7 will be used, and so on. In round 9, W36 to W39 will be used. Finally, as you can see that in round 10, there is no mixed column. There is no mixed column here, you see. SubByte, shift row, and add round key. Okay. So this is how our overall general structure of this AES, AES 128, we are actually discussing AES 128. Okay. So there are 10 rounds total. 10 plus 1 round is pre-round. This is pre-round. Okay. Pre-round. Now, whatever we have done for the inverse, actually ciphertext goes here as a input, and you reverse everything in the order, in the same order. Add round key, inverse shift rows operation has to be defined, inverse SubBytes has to be defined, inverse mixed columns has to be defined. Rest and round key will remain the same, so these keys are used in the reverse order, and then we get the plain text. So whatever can be designed here can be reversed also. Okay. So this is the whole overall picture of the AES 128. So let me now go into one by one in these details. What is SubByte, shift rows, and mixed column? Okay, and then finally we'll talk about key generation mechanism, key expansion algorithm. Now, before that, we will require some brief mathematical things, which I will just refresh. You already know these things, and also how the data structure will work here. So 128 bits means 16 into, so you remember 8 bits nothing but 1 byte, right? So 128 bits means how much? 16 bytes, right? Those 16 bytes will go as input as 4 by 4, as a matrix of 4 by 4. All these things we need to tell you. So data block viewed as 4 by 4, so 1 byte means 8 bits, right? 1 byte here, 1 byte here, 1 byte here. How many? This is 4 by 4 matrix of 8-bit values, right? So total, right? And this is known as word, or this whole column is known as word. Whole column or whole row is also known as word. Word, 32-bit words, 32 bits, because 8-bit here, 8-bit here, 8-bit here, 8-bit here. 8 into 4 is 32 bits total. Similarly, 8 bits here, 8 bits here, 8 bits here, 8 bits here, right? 32 bits. So each column or each row has 32 bits, which is essentially 4 bytes. Okay. Okay. So this is our 128-bit value is represented like this. So let me show you. One more thing. These 8 bits we break into two portions. So suppose we have 0 1 0 0 1 0 0 0. So you can see that 0 1 0 0 in hexadecimal notation, 0 1 0 0 is 4, and 1 0 0 0 is 8. So this is 48 as a hexadecimal value. So all these things, so 4 plus 4, 8 bits will be represented by, this is 8 bits and this is hexadecimal notation. Okay, this is how we these are all hexadecimal notations for 0 up to 9, and then for A B C D E F. 16 total possibilities. Okay, that's why it is known as hexadecimal representation of bit patterns. So this is what we are going to use here. Okay, so as I mentioned, 8 bits, these are 8 bits here, right? So either you look at row wise or column wise. This is known as byte. One word, okay, so 8 bits are known as byte, one word consisting of 4 bytes. So basically, 4 bytes, either this row wise or column wise. Okay, a block is nothing but you have the whole things are divided into blocks, so these are blocks of length 4, 4, 4, 4, 4, right, like this. So basically all of these things we can divide it into this state, and state is nothing but this kind of matrix, where each entry is, so this is 0, 0, 0 byte, 0, 0 byte, 1, 0 byte, these are the byte numbers, okay, or bytes basically. So we can actually, these blocks can be represented. So basically, if we have something like this, we can write down B0, B1, B2, B3, B4, B5, B6, B7, B8, B9, B10, B11, B12, B13, B14, B15. If something like this is written like this, okay. So this is a simple transformation. So we know what is the state here. So if text is this, hexadecimal values are this, so this is converted into a block. So this is state. Okay, state is all these hexadecimal values. So this is 4 by 4. Okay, and this is a byte here. You see, this is a byte here. This is a byte here. This is a byte here. All these are bytes. Any question at this point? Okay, so now we'll go into some more mathematical things. You remember Galva field having 2 raised power 8 elements is nothing but Z2x modulo a degree 8 irreducible polynomial, and in this case it is x raised to power 8 plus x raised to power 4 plus x cube plus x plus 1. I think you have to remember lecture 2 where we talked about finite field. So why we are looking at ZF28? Anyone can answer why we are looking at field with 256 number of elements, right? Galva field with 256 number of elements is 2 raised power 8. Okay, so this field we are going to use, and as you know, if there are two members, so there is either polynomial representation or binary representation of the field elements. If this is a field element, this is a field element, their sum is this modulo 2, everything is modulo 2, right? So you can easily compute. So 2 times x is 2 times x will be 0, so that is gone actually when you sum them. Okay, similarly in terms of bits, we can look at, this is a binary bit, this is a binary bit vector, and the sum is in the binary notation, and this is the corresponding hexadecimal notation. Okay, multiplication, so if we want to multiply, for example, you can see that hexadecimal values 57 into 83 is equal to C1. 57 is in terms of field element polynomial. This is a polynomial, you multiply, you get this, reduce it to modulo this is a reducible polynomial, remember, reducible polynomial, so you get something like this. So you reduce it, you get actually this is the final one, x is plus 7 plus x plus 6 plus 1. Okay, so which is nothing but C1. Okay, so this is how we do the calculations, multiplication. We also have multiplication by x. So if you multiply by x, actually it will become something like this. X is nothing but 02 in the hexadecimal, or in the binary notation it is like something like this. So again we can see that 57 into 113 is equal to FE because of this x time. X time means multiply by x. you shift it basically everything kind of once. So these are the calculations. I'm it's not very difficult, I think, but you should know how to do these things, as long as you remember the finite field business here. So finite field things you need to revise if you really want to understand. And we are in this cipher, we are in this block cipher, we are very only interested in field with 256 number of elements, because data is represented as byte strings, right? So that's why we are using CF228, right? Now let us look at details. So this is a typical round here. So state is going inside as 4 by 4 matrix. Then we apply SubByte operation. We get state. Again apply shift row operation. We get again a state. We apply mixed column. We get a state. Add round key. We get a state. Right. This is the typical thing. Only thing you have to remember, the first round actually, before first round, we only do one add round key only once, and ठीक है ना, and the third transformation is missing in the last round. So basically, mixed column is not there. Mixed column is not there in the last round. So remember, there is a pre-round, as I mentioned, then round 1 to round 9. So round 1 to round 9 is like this, and round 10, mixed column is not there. Okay, rest of things are there as it is. Now input bytes, these are the input bytes, state array and output bytes. Something like this will be the there, because 4 by 4 is going as the input. At any point, state array is 4 by 4, and then output bytes are 4 by 4. These are all bytes. Okay, so now we are ready to describe you what is SubBytes. SubBytes is a byte substitution. I can just create a lookup table, something like this here, and this is enough for us. But how to get this lookup table, I'm going to explain first. Okay, so it uses one S box of 16 by 16 bytes containing a permutation of all 256 8-bit values. Okay, so how to get this? So each byte of the state is represented by the byte indexed by the row left 4 bits and column right 4 bits. Example, byte 95 is replaced by byte in row 9 in column 5. So look at this, byte 95, row 9, column 5, row 9 and column 5. What is this value? 2A, you can see that, right? 2A. So here it is 2A, which has value 2A in this table, right? So how do we construct this table? Actually, this is what is important here. How do we construct this table? S byte means whatever is the byte here. So basically, I should say that whatever is a byte here in this state, when we do SubByte operation, look at this value. What is the value? Just now we saw that it was 95, right? So you take the 95, look at in the table, whatever is the value here, 9th row and 5th column, value was 2A. So we replace it with 2A. Okay, 95. This value was 95. We replace it with 2A using S box. So S box is this matrix table lookup. Okay, so the question is how to get this S box. That I am going to explain now. Otherwise, SubByte operation is very simple. So now, basically, SubByte operation can be defined algebraically also over this field GF 2 raised to 8, right? This is the polynomial as is used to build this field. You do this operation, x times SRC is the element in the matrix inverse this matrix XOR y. Y is a fixed transformation. So let me actually show you. Here is basically a matrix. So this is the value. So what we are happening, multiplying with x, and then there is a b. This is the input. What output is c. you just add this y value here, this vector here, and you get this desired column vector as the output. Okay, so let us see this. So let us show how the byte 0c is transformed into fe by the subbyte routine. Okay, and similarly you can transfer it back to 0c by the inverse subbyte operation. So the multiplicative inverse, we look at 0c. Multiplicative inverse of 0c in Galva field having 2 raised to 8 element is b0. Okay. Okay. So which means this vector b is this. Okay. Now once you have this b vector here, this b is known to you. You insert it here, multiply with this fixed matrix X of this kind. Okay. Then you get C. In this C vector, you add this vector, this fixed vector y, which is 1 1, this kind of fine transformation, you know, and then you get output as d vector. So as you can see here, the result is multiplying matrix X by this matrix results in C vector as this, and result of XOR operation is d is equal to this. Okay, which is fe in hexadecimal. Okay, so now as you can see that, so basically b0, when b0, why when b0 is b, because this is 4 hexadecimal, right? This is capital B and this is 0. Capital B is 1011 and 0 is 0000. Similarly here, D means this portion here is F and this portion here is E. Okay, so this is how we look at. So basically what we are looking at, for each entry, we are looking at the multiplicative inverse in the Galva field having 2 raised to 8 elements, and then multiplying it with X matrix. Whatever result is coming, we are subtracting this fixed Y. Okay, multiplying with X, whatever result is coming. Okay, we are adding this vector here, and then that is the output here, D vector. Similarly, the reverse, I'm not discussing the reverse, but you can see how the reverse will go. Okay, so this is a sub-byte operation. Similarly, there is an inverse sub-byte operation. So rather than doing all these things as a programmer, you don't have to worry about these operations. You can simply use lookup table. Okay, so this lookup table is enough for you. So whenever there is an entry here, you just look up the table, and I'll show you another example again. For example, you see here, look at say 1 2. I want to sub-byte operation 1 2. What should be the 1 2? You look at row 1 and second column. Row 1, row 1 and second column. The value is C9, right? So the value is C9 here. See? So this is how every hexadecimal value is converted into this thing by simply a substitution. That's why it is known as sub-byte substitution. Okay, sub-byte transformation by from the lookup table. Similarly, for the inverse sub-byte, we have the inverse table here. This is inverse table here, which we can use. Okay. Any question in this sub-byte transformation? So I hope this is clear to you. There is some algebraic way, but you know, simply we have to only worry about the lookup table. Okay, this is sub-byte operation. So now what is left here? I told you about sub-byte operation. Now, so state was 4 by 4 matrix consisting of hexadecimal values of bytes, and the output is 4 by 4 matrix consisting of hexadecimal values of bytes. Now I have to apply shift row operation. What is shift row operation? Shift row operation is not very difficult, but I should say you. So shifting, which permutes the bytes. So you know, so when a matrix like this is entered, first row is unchanged. You can see that whatever is the first row combination, same combination is here. Second row does 1 byte circular shift to left. You can see that this is shifted here, this is shifted here, this is shifted here, this is shifted here. This is one shift. Okay. Then 2 shift and 3 shift, like that. Second row does 1 shift, third row does 2 shift, fourth row does 3 shift. Okay, so this is a circular byte shift in each case, right? So in the encryption, this transformation is called as shift rows. You have to shift the rows. First row, no change. Second row, one shift. Third row, 2 shifts, and last row, 3 shifts. Okay. Similarly, the shift is this right here. The shift was shift to left. When we do shift to right, we get inverse shift rows. Which is a straightforward operation. Okay. So this is shift row. So let me. So here is. So if something like this is there, right? The shift row operation. First row, as you know, there is no change. Second row is shifted once. Third row shifted twice. Last row shifted thrice. So this is how we shift from here to here. Similarly, we can go back. Okay. When we can come back, we can go back by inverse shift row. Okay. Shift rows. Okay. So here is the actual value. You see that this is the hexadecimal values in the state. First, there is no change. Second, there is 1 shift, 2 shift, 3 shift. Okay. This is shift row operation. Now now we have third one, which is known as mix column. So I talked about SubByte operation, where whatever is the value in the matrix is replaced by the corresponding lookup table. Shift row operation. First row no shift, second row 1 shift, third row 2 shifts, and last row 3 shifts. Now we'll do the mix column operation. This is also a pretty interesting thing. Okay, so what is mix column operation? So shift row and mix column provides diffusion to the cipher. Each column is processed separately. So basically what is happening, this is you take one column, multiply it with a constant matrix, and do this transformation. Basically everything is done over this field GF28, right? Okay, so basically I can show you in a very specific manner how this happens. We don't have to do all these things. So here you take so basically you fix this constant matrix, something like this: 2 3 1 1 1 2 3 1 1 1 2 3 3 1 1 2. Okay, now so basically if your first column, so this is our state matrix. Take the first column, which is S00, S10, S20, S30. You put it here, multiply it with here, you get something here, and that is your output. The first output here, this one. Similarly, take the second column, put it here, multiply, and do the simplifications. You get the second column. You take the third column, you get the third column. You take the fourth column, you get the fourth column. Okay, so this is how you do the mixed column transformation. Okay, by using this matrix. Let me show you. So we are taking this column here, multiplying with that matrix, and then simplifying it, and then we are getting this one. Okay. Similarly, we can go back. We can come back, we can go back. So remember how we need to do? Multiply with this matrix here, and then you do the calculations. Finally, we can talk about AND round key. So XOR stayed with 128 bit of round key. Okay. So add round key proceeds one column at a time. So basically, let me show you. So these are the round keys. So if you remember, I think I can show you that first picture here. Yes, these are the round keys, W0, W1, W2, W3. Similarly, all of them. So from one cipher key of 128 bits, one cipher key of 128 bits. Be carefully, listen it very carefully. One cipher key of 128 bits. So basically that means how many bytes here actually. So we get 44 such of things. 44 such keys, round keys. Out of this, first 4 round keys are used here in the pre-round. Rest of them are used here. The 40 keys are used here. Okay. So how this round key operation is done? So let me explain to you this round key operation a little bit more. So this is the state vector. So round keys, as you know, so each wi, so we can say this is a 4-byte vector, right? Wi's are the words. You remember, wi's are the words. If you see here, these are words. So w1, we can say that w0, w1, w2, w3, right? All these 128 bits we are broken like this. So key is something like this. Okay. So first one is say w0, then w1, then w2, then w3, right? So w0, w1, w2, w3 is the first round, pre-round. Then first round will be w1, w2, w3, sorry, you just take the next one, w4, w5, w6, w7, and so on. Okay. So this is what is happening here. We are adding these column corresponding to each column here, and we are getting the result. Add round key. Wi is added here, wi plus 1 is added here, wi plus 2 is added here, wi plus 3 is added here for each I, starting from I is equal to 0, right? So here is the whole scenario. AES round. So state, SubByte operation, you get a state. Shift rows operation, you get a state. Mix column operation, you get a state. And add round key operation, you get a state. This is the whole AES round. Okay. Got it? So this is the whole general scenario what is happening. Remember, state is a 4x4 matrix. Okay. Now let me tell you something about the round key, AES round key. I mean AES key expansion algorithm. How this, we take 128 bits. So basically, 128 bits means 16 bytes we are taking in the form of a matrix. Remember, 4x4. So 128 bit values. Now we take these keys here, K1, K2, K3, and so on, K16 bit values, and expand it into 44 words. So what we do is start by copying key into first 4 words, then loop creating words and depend on the values in previous and 4 places back. In 3 or 4 cases, just XOR these together. First word in 4 has rotate, SBox, and XOR round constant. Round constant is what is there. These things let me explain to you. Here is a key expansion. So these keys are here in the 4x4 array, and then you add them. Okay, then there is a function G which is operating, which is a very special kind of function, and then you get the next round of key. So let me see. So here is a pre-round keys, then round 1 key, round 2 keys, and so on for each round, whatever is NR. So NR in our case will be 10 for AES 128. Okay. Okay. So these keys are generated. So this here is a thing, we use rotation word, sub word, and these arc on value. From cipher key, we generate whole thing. So let me give you an algorithm actually. Basically, rot word is rotation word, it will rotate something like this. Subword is performs a byte substitution in each byte of input word using an S box, and subword rotation word temp is ZORD with archon values. What are these round constants values? So here is the round constant values, in hexadecimal notations. This is 0, 1, 0, 2, and then all these things 0, 0, 0, okay. So they are generated like this, round values. Everything is defined over G of 20, G of 28, But let me show you the lookup table, Here is, or I should summarize, here is a algorithm for key expansion. So these are the values which are constant. You can assume that, okay. These are the constant values of archon values. And then you do these things, okay. Subword substitution of the rotation word, and then use this, sum them with archon value. Okay, this will generate a temp value, and this temp value is added in these WIs to get you W0 to W43. All these 44, things are generated actually, right? So this is the key expansion thing, you know. So normally everything. So although there is a mechanism to generate these archon values, but actually everything is done from the point of view of lookup table. That is what is the key thing. So now let me show you an example here. So plain text is this, cipher key is this, and cipher text is this. Here is the example: pre-round, initial output, output state, round key, round 1, round 2, round 3, and so on. We'll have round 10, and finally, we have the output. These are the state in input state, after SubByte, after shift rows, after mix column, output state. So that's all. So I think I should mention some of the security things. AES was designed after DES. Most of the known attacks on DES were already tested on AES. AES is definitely more secure than DS due to the large key size. So brute force attack seems to be impossible. Statistical attacks like numerous tests have failed to do statistical analysis of the cipher text. Differential and linear attacks, there are no differential linear attacks on AES as yet, So this is all open, Implementation aspects, the algorithm used in AES are so simple that they can be easily implemented using cheap processor and with a minimum amount of memory. Very efficient. Implementation was a key factor in selection as the AES cipher. I think that's all. So if you have any questions, please do ask. This was an interesting thing. So I hope again I can just show you main. I just repeat. This is the whole structure of AES 128. We have this, rounds, pre-round transformation, then round 1, round 9, and then round 10. Mixed column is not there, right? And then we can reverse everything in the same order, in the reverse order actually. Okay, and there are key expansion algorithms for generating these keys, which we are adding column wise to the state vectors, state matrix. Any question now at this point? Any question? So each round has 4 things: SubByte, shift rows, mix column, add round key. Except last round where there is no mix column. Okay, so I think if there is no question, that's okay. You can stop.